What's up, everyone? So, we've been talking about thermodynamics in chapter 3, and I have emphasized that thermodynamics that deals with energy is really important because the energy is the currency in the cell processes, right? You need energy or produce energy when you have these cell reactions that are happening. So, we've looked at how to calculate these energies and a lot of things that happen in terms of these high energy particles. But one last thing that I want to talk about is thermodynamics and how it relates to reaction potentials. And why is this important? This is important because the reaction potentials involve the transfer of electrons, and the transfer of electrons is electricity, and this involves energy as well, and there are a lot of reactions that work like this. So we need to know about this, and this is a little bit of a review from um, Gen Chem 2, but we're going to relate this to the biological processes. All right, so first of all, when you're talking about reaction potentials, we talk about redox reactions. What are redox reactions? These are reactions that are paired, and they are paired with oxidation and reduction. All right, so we need to know what oxidation and reductions are. Oxidation is the loss of electrons. Reductions, the gain of electrons. And these are coupled together, right? So these are not two reactions. It's one reaction that involves a loss of electrons and a gain of electrons, right? So we need to know in a redox reaction what entity is losing electrons, what entity is gaining electrons, right? So this is another way of representing it, and a lot of people get confused by this. So if you have oxidation, again, you have a loss of electrons, but the agent that's undergoing oxidation is called the reducing agent. The agent that's undergoing reduction is an oxidizing agent. And it is an oxidizing agent because even though it's undergoing reduction, it's oxidizing the other compound. So you have compound A going through oxidation by losing electrons, and it's a reducing agent, and it is oxidized, right? Compound A gets oxidized by losing electron, and it is a reducing agent. And compound B gets reduced, goes through reduction, and it's an oxidizing agent. Make sure that you can tell the difference. And how does it look like in a chemical reaction? This is an example of what we call an electrochemical cell or a galvanic cell. How does this work? This is a very beautiful way you can use a chemical reaction to drive electricity, to produce electricity. And how does that happen? We are, as we said in a redox reaction, one compound loses electrons and the other one gains electrons. So we have a movement of electrons. And the definition of electricity is the movement of electrons. So why not take advantage of this movement and just put a, in this example, you put a light there and it's going to give you electricity, right? So this is how batteries work. This is how batteries in your phone work because of electrochemical cells. We're using redox reactions. We're using this movement of electrons to produce electricity. Now, this example, you have zinc and then you have copper. Now, this is an electrochemical cell, and these two parts right here, we call them half cells, right? we have two half cells. So you have the zinc half cell, you have the copper half cell. Now, this is a redox reaction. And as you can see here on this side, zinc is becoming zinc 2 plus plus 2 electrons. Zinc is being oxidized. You have oxidation. But what about copper? Copper is going from copper 2 plus to copper. It's gaining electrons. It's being reduced. You have reduction. So you have two what we call electrodes, right? Here, this electrode here is called a cathode. So reduction at the cathode, oxidation at the anode, right? These are the two half cells that we have, right? So when it comes to half cells, we're gonna need to know the potential. What is the potential between the two half cells? Now, you see where the light bulb is? You can put a voltmeter and measure the potential, but you can also calculate the potential, right? So from this, you have copper, which is being reduced, and then you have zinc that is being oxidized, right? So here, you can measure the potential by knowing what we call the standard potentials, right? So the standard potential, you're going to get a table like this where you can find the standard potential. So here, copper, the standard potential of copper, right? Copper 2 plus plus 2 electrons is 0.34, and zinc is negative 0.76. But I want you to pay attention. I really want everybody to pay attention here. The way our reaction is, right? Copper is undergoing reduction. So from this table, this copper is going to be plus 0.34, no problem, because it's undergoing reduction. But zinc is undergoing oxidation. Is undergoing oxidation, but in the table these are reduction potentials. So the potential you get for zinc here is for reduction. You can't use this here because zinc is undergoing oxidation, so you're going to use the reverse of that, right? So you're going to get 0.34 for copper, but for zinc is going to be the opposite of the reduction potential because this is oxidation. And this is how you find the total potential. You take this plus this, but after you've written the half cells correctly, right? And here you write down the total, right? You can write down the equation making sure that the electrons cancel. So this is how you find the total potential of an electrochemical cell. Why is this important? It's important because the potential of an electrochemical cell can be used to find the delta G. The delta G of a reaction. So the delta G of a reaction is negative N, which is the number of electrons. So in this case, the number of electrons is 2 electrons. So you can get delta G naught is going to negative N. F is the Faraday constant. The Faraday constant, I think, is 96500 amperes per mole, but it's going to be given to you, and then the standard potential. So the standard potential we've calculated here, you can just find the delta G of this reaction right here by just taking negative 2 times the Faraday constant times this number right here, 1.1 volts. And you're gonna get the delta G of the reaction, right? So that's the beauty of finding the voltage of a reaction, is because you can find the delta G of a reaction. Now, these examples that I gave you is just zinc and copper, things that we do in the lab. But when it comes to biochemical processes, you can do it too as well. This is an example that we do in the lab where you can use in a system where you have acetaldehyde and ethanol, or even fumarate and succinate couple. And this is because fumarate and succinate is a known redox reaction in the cell, right? There are other redox reactions in the cell. So I gave you one in the PowerPoint and in the book where these are examples of redox reactions. And as you can see, you start to see some of these that are familiar, right? Like the FAD example, the pyruvate, the, NAD plus. So these are redox reactions that make the cell pretty much function. And we'll talk more about some of these. So I'm going to give you some like this, where I ask you a question. I give you, starting with the standard free energies given in the text, calculate the delta G and the potential for the cell, for the following reactions. And I give you some like this. So this is a total reaction, right? So I gave you, let me see if I can show you my paper. All right. So Ag plus Fe3 plus gives us Ag plus Fe2 plus. All right, so if we look at this, it's pretty easy to start to see, okay, Ag became Ag plus. So did Ag lose electrons or did Ag gain electrons? Ag lost electrons, right? When something becomes more positive, it has lost electrons. When something becomes less positive, it has gained electrons. And this is because electrons are negative, right? So you can, from this total equation, you can isolate the half equations for each one of them. So this one, you can say that you got Ag became Ag plus 1 electron, and Fe3 plus gained 1 electron to become Fe2 plus. Right? It's pretty easy. We just isolated the two. And after isolating the two, how do we find the potential? Let's look at the table. The table should contain these two. So the table has Ag to Ag plus. Do I have it? Yes. So so this is another example. The table has Ag plus to Ag. The table has the opposite, right? So if you look at our equation right here, Ag undergoes oxidation, this undergoes reduction, right? And the table, we already seen that the table shows us the reduction potentials. So whenever you have oxidation, it's the opposite of reduction. So here you have Ag, which is plus 0.8. We're going to have here negative 0.8 volts, because this is the opposite of what we have written as reduction, because this is oxidation. But that's for Ag. For Fe, that's iron, it's written as such, right? Iron 3 plus becomes iron 2 plus, and it's 0.77. So we put plus 0.77 here. All right? So this is easy because you have 1 electron here and 1 electron here, so that they just cancel. One thing is, whenever you solving these equations, make sure that if you don't have the same number of electrons here, you're gonna have to multiply the number here or here to get the same number of electrons. But even though you might have to do that, even when you multiply the number of electrons here to get you might multiply the stoichiometry to get the same number of electrons, but it shouldn't affect the voltage here, right? The voltage doesn't care about the stoichiometry, it's still the same voltage. So here, the electrons cancel. You end up with Ag plus Fe3 plus gives us Ag plus Fe2 plus, which is what we started with anyway. And the total here is going to be equal to, should be 0.03 volts. And this is the voltage, right? This is the voltage that we've been looking for, delta E prime. That's the voltage that they asked. Now they say, okay, find delta G. We can find delta G because we have we do have the voltage. So if you remember, the formula is delta G naught is equal to negative NF delta E, right? And we know that here delta E is 0.03 volts, so delta G is negative N. The N here is the number of electrons, so you have one electron. So 1 times Faraday, the Faraday constant is 96500 per mole, times delta E, which is here negative 0.03 volts, right? And you just multiply, and should be 2895 joules per mole, or 2.895 kilojoules per mole. That's delta G. Here is something else that I can ask you after you got delta G. I can also ask you the equilibrium constant of this reaction. If I ask you the equilibrium constant of this reaction, you can't be able to do it because remember this equation that we've seen earlier in the chapter where delta G naught is equal to negative RT ln of K. So if you got delta G and I gave you the temperature, you can get K. So let's say this is room temperature. Room temperature in Kelvin. This needs to be in Kelvin because we have R in Kelvin. So can you find K? Yes, you can find K. And look, delta G is here. R, we know it. T, we know it. You just solve for K. And you can solve for it manually, but I'm going to give you a quick formula that you can use, where you can say that K is equal to E to the, let me see, negative delta G naught over RT. This is what K is going to be equal to. And you can use this formula to find K. So by just measuring the voltage on a reaction, we're able to find delta G, which is the free energy of a reaction, meaning we can know whether or not something is spontaneous or non-spontaneous, and we can measure the K, the equilibrium constant, right? As long as we can measure the temperature, and we can measure the temperature, all you need is a thermometer for a reaction. So this is really cool. Now I can give you a reaction like this, right? But I can also give you a reaction like this, where it's a biochemical reaction, where it's like NAD plus isocitrate is equal to NADH plus H plus alpha ketoglutarate plus CO2. And I ask you, okay, the same thing I asked you above here. What is the delta G? What is the delta E? And what is the KEQ, the equilibrium constant for this one? If I ask you that, it's the same idea. This is a total overall reaction. All you need to do is divide this into individual reactions, right? And how do we divide this into individual reactions? You find in the table. You find it in the table, right? So this is the table from your book. And again, we have isocitrate, and then you have NAD plus. So let's go back. Look, you have the NAD plus here, the NAD plus reaction here, and the isocitrate reaction here. And check this out. NAD plus is going forward, right? NAD plus is NAD plus giving you NADH plus H plus, but isocitrate is reverse. What does that tell you? It tells you that NAD plus is going through reduction, because these are reduction potentials, and an isocitrate is going through what? Oxidation, right? And it's telling you that now you know that the half cell for NAD plus will be written as it is. The isocitrate is reversed. So let's write it down and see what we got here. So we got NAD plus isocitrate gives you NADH plus H plus alpha ketoglutarate, and then plus CO2. There's a lot. But that's okay. What we need to do now is go back to the table and find the half reactions. The first half reaction involves NAD plus. So the half reaction is NAD plus 2H plus 2 electrons is equal to NADH plus H plus. So I'm going to write it down. That's the first reaction, the first half reaction. And the second half reaction is this one, alpha ketoglutarate, right? This one, alpha ketoglutarate plus CO2. But this one is going to be reverse, right? Remember that. So it's going to be equal to isocitrate equal to alpha ketoglutarate, that's alpha keto for short, plus CO2 plus 2H plus 2 electrons. Right, these are the two half equations, right? These are the two half equations that cancel out to give us this overall equation. Now let's look at the potentials. NADH, the potential for NADH is written as negative 0.320, right? So that one is just negative 0.320 volts, right? But the second one is the one that's reversed. this one right here is reversed. So instead of being negative 0.380, it's going to be positive, right? Positive 0.380, because this is oxidation. And again, the total, if you can see, these 2 electrons will cancel with 2 electrons. This is 2H plus will cancel with these 2H plus. And the total will be just like it's written up here, where it's 8AD plus isocitrate becomes 8ADH plus H plus alpha keto plus CO2. Beautiful. Now, what's the voltage for this reaction? Well, you add these two together. So the voltage here, delta E naught, is 0.06 volts. That's it. That is it. Now, can we find the delta G? Yes, we can. Delta G naught is equal to negative NF delta E. And here N is the number of electrons exchanged. Here you have 2 times F, which is 96500. And delta E is 0.06 volts. Alright, and this is going to be equal to negative 11580 joules per mole, right? And remember that after this we can even find the K, right? And the K is, again, K is equal to e to the negative delta G over RT, right? So if you're given the temperature, you can find the K, no problem, all right? So that's how you find, when given an equation, that's how you find the potential, that's how you find delta G, that's how you find K. Make sure that you know how to practice that. Alright, so now after we find this, I'm going to take you to a next level where sometimes you might not have standard conditions. A lot of times you won't have standard conditions for potential, right? So you might have to find the potential of the cell given non-standard conditions. So what does that mean? It means that usually whenever you give the standard potential, we assume that everything is at 1 molar. We assume that everything is at 1 molar, but sometimes it's not at 1 molar. We're going to have to calculate the new standard when it's not at 1 molar. So we take concentration into account. So the standard of the cell is going to be equal to the standard potential that we calculated minus RT over NF, which are all pretty much constants, times ln of Q. And ln of Q is the quotient. This is the concentration quotient, right? And in this case, another way we show it is the concentration of the oxidized over the concentration of the reduced, right? So this is called the Nernst equation, and this is very, very useful, and it's used a lot because, again, in a lot of cell conditions we'll have differences in concentrations, right? So that means that, for example, if we go back to our cell, right? So if we go back to our cell, for example, here of copper and zinc, we find the potential assuming that we have 1 molar for each. But if we have a different concentration of copper and zinc, right? Remember that zinc is oxidized, copper is reduced, right? So we're going to take the concentration of zinc and the concentration of copper into account because it's different from 1 molar. So if you had to do the Nash equation for this, you're going to, so we already found the potential, right? The standard potential, which is 1.1. So here we're going to take 1.1, right? The 1.1 we just found plus R times 2 over N and F times ln of the concentration of the oxidized over the concentration of the reduced. So in this case, the oxidized is zinc, the reduced is copper. So the concentration of the zinc 2 plus in water and the concentration of copper 2 plus in water. So if you are asked to use the Nash equation, you're going to be given the concentrations, right? But if you are just asked to find the standard potential, you find the standard potential as usual like this. But now you know how to do both. All right? And I think that's enough for what we'll be calculating in this chapter. Reach out to me if you have any questions. I'll see you. Bye-bye.